For, well, forever, building our most complex machines, things like rockets, has been this incredibly slow, painstaking, manual process. But what if that entire way of doing things is about to fundamentally change? I mean, think about it. What if instead of an engineer sitting there clicking and dragging to draw a part, you could just write the logic that creates it? What if you could design, build, and test a brand new rocket engine, not in years, but in just a few weeks? Well, this isn't science fiction. It's the revolutionary idea at the very heart of a company called Leap 71. To really get why this is such a huge deal, we first have to talk about the massive bottleneck that's been holding traditional engineering back for decades. This comparison really lays it all out. On the left, you've got the old way. It's all manual drafting, right? Every little change is slow, it's expensive, and frankly, it's a pain. But then you look to the right. This is the new paradigm, completely unlocked by code. It's not about designing the object anymore, it's about designing the logic that creates the object. That's a huge shift in thinking. And that's exactly what computational engineering is. So instead of an engineer spending hundreds of hours meticulously modeling a single component, they write a set of rules, basically a recipe or an algorithm, that can then generate thousands of different variations automatically. It completely transforms the role of an engineer, from a kind of digital drafter into a true system architect.
So how does this actually work in practice? Well, Leap 71 didn't just have an idea. They've built an entire vertically integrated software stack to turn this concept into hardware.
You can think of it in three layers. At the very bottom, you have the foundation, PicoGK. It's a powerful open source tool that can handle the incredibly complex shapes you need for things like rocket engines. Then, sitting on top of that is Neuron. This is the brains of the operation. It's a massive computational model that understands physics, engineering principles, and even the specific limitations of the 3D printers being used. And finally, at the top, you have specialized models that take all that brainpower and apply it to a specific task, like designing rocket propulsion systems. And this description of Neuron really gets to the point. This is not just an AI assistant that suggests a few changes here and there. Nope. Neuron takes the high-level requirements, things like thrust, what propellant to use, what pressure you need, and it autonomously generates a complete, totally manufacturable design from scratch. Now, that is a bold claim for sure. But here's the thing. Leap 71 has the proof. So let's get to the really cool part and see how they went from just an idea on a computer to a real working rocket engine firing on a test stand. Less than 3 weeks. Let that sink in. That's how long it took them to go from getting the initial design specs to a successful hot fire test. In the traditional aerospace world, a development cycle like this takes many months, often years. This kind of speed is a complete and total game changer. And this wasn't just some simple one-off engine test. In this single, super-fast campaign, they designed and tested 2 very different engines. Both used modern Methalox propellant, produced about 2 tons of thrust, and were fully 3D printed out of a high-performance copper alloy. And the most important part? Both designs were generated 100% by the Neuron model. The first engine was a classic, the conventional Bell nozzle. This is the workhorse of the rocket industry, the design you see everywhere. And it performed beautifully, hitting over 93% combustion efficiency on its very first test run. This just proves that the physics models baked into Neuron are incredibly accurate. But the second engine was something way more exotic, an aerospike. Now, this design is theoretically much more efficient, but it is notoriously, ridiculously difficult to build. So hard, in fact, that one has never actually made it to space. The fact that the same core logic from Neuron could generate this radically different, super advanced design is just astonishing. And for Leap 71, this isn't just about showing off. As co-founder Lynn Kaiser explains, these real-world tests are a critical feedback loop. All the data they collect on temperature and pressure gets fed right back into Neuron, which makes the model smarter and more accurate for the next time. It's learning from experience. So, they've proven the concept works, and it works at incredible speed. What's next? Well, scaling up, massively. This timeline really shows their incredible momentum. In just about 18 months, they've gone from a 5 kilonewton kerosene engine to a 20 kilonewton methane engine. And they are not stopping there. The goal for 2026 is to test engines in the 200 kilonewton class. That's 10 times more powerful. And they're already validating the manufacturing for engines that are even bigger. I mean, look at this thing. This is an injector head for a 2 times meganewton engine. That is the same power class as the engines on today's heavy-lift rockets. It's huge, 600 millimeters in diameter, and it was 3D printed in under 4 days. That's just wild.
And this technology is already being put to work on real-world projects. Leap 71 has partnered with Aspire Space to develop those 200 kilonewton engines for the second stage of the Oryx rocket ship, a really cool next-generation, fully reusable launch vehicle.
So this incredible speed and scale has profound implications, not just for building rockets, but for the very nature of engineering itself. Just look at this shift. An engineer's primary task moves away from the manual labor of 3D modeling and towards the creative, high-level work of creating and refining design logic. Instead of painstakingly redesigning a part, you just change a parameter in the code and recompute. The engineer is elevated from a model drafter to a true system architect who can explore a design space that was previously just unimaginable.
And this is a really important point, this doesn't mean the human engineer becomes obsolete. Not at all. As CEO Josefina Lissner says, this whole system is built on a foundation of deep, real-world engineering knowledge. The AI is incredibly powerful, but it's really just encoding human expertise. Neurons' predictions have to be absolutely perfect to create hardware that actually works under the extreme conditions inside a rocket.
So what we're witnessing is a fundamental shift from manual design to algorithmic creation. And it leaves us with one heck of a fascinating question. If this approach can radically shrink the timeline for building something as complex as a rocket engine, what other industries is it about to completely transform? What will code build next?